So, as promised, um, recording a lecture to cover the material that is near the end of chapter 4 in the textbook. And we're going to continue looking at this natural coordinate version of the equation of motion in the n hat direction. Okay, so this is the normal direction, points to the left of the wind, and we have three terms. If we look at this in terms of the force balance, we have the centrifugal force, so minus v squared over r, where r is the radius of curvature. We have Coriolis, minus F times V. And we have the pressure gradient force, which we're writing in terms of the geopotential gradient, d phi dn. Now, each one of these, even though there's a minus sign out front, will be considered positive if they are acting in the plus n hat direction. The velocity, the wind speed, will always be positive, or I guess it could be zero, but it cannot be negative. And since that's the case, the Coriolis acceleration, by definition, at least in the northern hemisphere, will be negative and will act in the minus n hat direction. That's always going to be the case as long as there's some Coriolis acceleration to consider. But the other two terms could be either positive or negative. It just depends. For the centrifugal force, it depends on the sign of the radius, and the radius can be positive or negative. And so the centrifugal acceleration could point in the plus or minus n hat direction. And same thing with the pressure gradient force. That could be positive or negative, and it just depends on the gradient. It depends on the orientation of the geopotential height field compared to the wind. So I'm going to use these symbols and colors to denote these different forces or accelerations when we look at these terms as a force balance diagram. So the pressure gradient force is going to act from high to low. And that, again, that could be in either the plus or minus n hat direction. I'm going to set this up so that the wind is always blowing from left to right. And since we're using natural coordinates, we just have to rotate our perspective for this to be valid, and it should always work. And so the Coriolis force is always going to act to the right, at least in the northern hemisphere, and that's in the minus n hat direction. So I'll use this orange color for the that particular force component. And then the centrifugal acceleration will act outward from the flow curvature. And so here you're going to see these arrows that are curved, and this indicates counterclockwise turning. And when we have that sort of flow curvature, we denote that the radius of curvature is positive in that situation. And then the centrifugal acceleration acts outward, which is in the minus n direction in this case. And we could also have clockwise turning flow, which if we measure the radius to the center of that curvature, we define that as negative radius. And the centrifugal acceleration acts outward from that turning, and that's in the plus n hat direction in this example. So we just need to get comfortable with whether these individual components of the forces are acting in the plus or minus n hat direction, or acting to the left of the flow or to the right of the flow. But the result needs to be a balanced situation. So we're that's our starting point, is that all these things must balance out, and so whatever net force is acting to the right, there should be an equal and opposite combination of forces acting to the left in these situations that we're going to analyze. So just to get the radius of curvature nailed down here, if we have counterclockwise turning, we define, and we want to actually come up with a radius of curvature, we would fit a circle to that flow curvature and then measure the radius of that circle. You don't always get a perfect circle with the real flow, so you try to fit the circle in the vicinity of the actual wind that you're analyzing as best you can, and then measure the radius of that circle. And if it's counterclockwise, we define that as a positive r. And then the opposite is a negative. If the flow is turning clockwise, we fit a circle to that flow pattern, especially in the vicinity of the actual wind that we're looking at, and define that as a negative radius. So whatever distance that happens to be, we call that negative, because it's basically pointing in the minus n direction. There's some other important notation for these types of turning that we're going to start using. Cyclonic means that the rotation is in the same sense as the Earth's rotation. And so if we're standing on the North Pole and observing the rotation of the Earth, we would notice that it's rotating in a counterclockwise fashion. And so any flow curvature that is counterclockwise we call cyclonic in the northern hemisphere. And then the opposite would be anticyclonic. So clockwise turning is anticyclonic in the northern hemisphere. Now, you need to convince yourself that the opposite is true in the southern hemisphere. Clockwise is actually cyclonic and counterclockwise is anticyclonic when you're standing on the South Pole and noticing the rotation of the Earth. But for the most part, we're going to be focused on the northern hemisphere. And so cyclonic, counterclockwise is positive radius, anticyclonic, clockwise flow is negative radius. And so our force balance diagram should end up looking something like this. We will note the orientation of the rotation or the turning. And again, in this situation, it's counterclockwise, which is a positive R. We'll note the sense of the pressure gradient. And so in this case, lower pressure is to the left, so the pressure gradient force should also point to the left. And Coriolis will go to the right in the northern hemisphere. Centrifugal will go outward from the turning. And so we should have a situation where these forces balance, and the net combination of forces acting to the right should balance out those acting to the left. But they're not always going to be in this order. And we can have a variety of combinations of all three of these, centrifugal, Coriolis, and pressure gradient force, depending on the situation. And so we started looking at a simplification where the flow is straight and the radius of curvature would be infinite in that case. So since that's in the denominator of the centrifugal acceleration, that term is 0. And what we end up with is a balance between the Coriolis and the pressure gradient forces. So if F is greater than 0, which it is in the northern hemisphere, we should see the Coriolis force acting to the right and the pressure gradient force acting to the left. And those should be perfectly balanced. And that's what we see when we assume the flow is geostrophic. So again, this would be for perfectly straight flow, and the height contours in this case would just be straight lines with lower heights to the left of the flow. And we can rearrange this to solve for V, and that's what we call a geostrophic wind. And we also talked about the situation where, let's say, there's no pressure gradient. So dphi dn is 0, there's no pressure gradient force, but there is some velocity. So say we've been able to set the flow in motion somehow, but there's no pressure gradient force. Since V is greater than 0, we're going to have some centrifugal acceleration and some Coriolis, and those have to balance each other out. So really the only way for this to work, since in the northern hemisphere Coriolis acts to the right, is for the centrifugal to act to the left and balance that. And the clockwise or anticyclonic flow is the only solution that will work. So we need to have a negative R for this to balance out, and that's the type of turning that we would expect to see in this case. And it makes sense. If we've set something in motion, Coriolis should act to the right. It should just be a continuous right turn, and we see this sort of circular, repeating, oscillating flow in this type of situation. Now the next approximation is, what if the Coriolis force is really small? So let's say we're looking at the low latitudes where F is close to 0 and the Coriolis acceleration is tiny or 0 or small enough to neglect. This might also be the case where we're looking at a small radius of curvature and the centrifugal acceleration is really large, and relative to Coriolis, it's a much more dominant term. Then we're looking at a balance between the centrifugal acceleration and the pressure gradient force. And so we can rearrange this and solve for V, and we see it's the square root of minus R times dphi dn. And this can have actually two possible solutions. And so we can have a cyclonic circulation. We can have this counterclockwise turning where the radius is positive. And if r is positive with this minus sign, that means d phi dn must be negative. And that's the case. We have lower pressure to the left in the n direction. So d phi dn is less than 0. And we would have this cyclonic turning of the flow where the pressure gradient force is balanced with the centrifugal acceleration. And the flow is acting in a cyclonic sense. However, we can also have an anticyclonic turning in this situation. So this clockwise turning would give us a negative r. So if r is negative, we actually, this is incorrect. With this minus sign, we would need d phi dn to be positive, and that's the case here. So the flow is pointing, in this case, from right to left. And so the n direction is down in this particular example. And so d phi dn positive means the higher pressure is on the lower side, and lower pressure is to the right in this particular example. And so this should say d phi dn greater than 0. But we still end up with low pressure in the center of this circulation. It's just an anticyclonic circulation where, again, the pressure gradient force is balanced with the centrifugal acceleration, which is outward. But the velocity is now going from right to left instead of from left to right. And this hopefully makes sense. Since there's no Coriolis, it doesn't really matter which direction the velocity is going here. We just have to have these two forces in balance, the centrifugal and the pressure gradient force. So the cyclostrophic flow, again, is observed where we have relatively small Coriolis acceleration and relatively large centrifugal acceleration. So the radius of curvature is probably small. And we can look at the Rossby number in this case. We can look at the ratio of the acceleration to the Coriolis. And the acceleration is the centrifugal acceleration, v squared over r. When Coriolis is fv, the minus signs cancel in this case. And we can cancel out one of the v's. So that Rossby number is v over f times r. And for cyclostrophic flow, both r and f are relatively small. So the denominator is small, the Rossby number is large. And so cyclostrophic flow is what we observe if the Rossby number is large. And tornadic flow is a good example. It's usually what we use to demonstrate this particular balance. So if we look at the tornado example, rounding all these things off to the nearest power of 10, the wind speed 100 meters per second is not out of the question. If you look at the mid-latitude Coriolis parameter, 10 to the minus fourth, and a radius of curvature for tornadic circulation of a kilometer or 1,000 meters is also not too far off. And so looking at the Rossby number for the tornado situation, we see we get 1,000, which is a large Rossby number. When we're talking about mid-latitude geostrophic type flow, we're looking at a Rossby number of around 0.1. So this is much, much larger than that. It indicates the huge importance of the centrifugal acceleration in that particular case. And so if we had that type of 100 meter per second velocity and 1,000 meter radius of curvature, we could plug those numbers in and calculate the pressure gradient in that situation and see the type of pressure gradient that we would expect in a tornadic circulation. That's something I'm going to ask you to do in the next homework. So moving back to sort of the larger scale flow and the relationship between the winds and the pressure gradient. This is the 500 millibar heights just from a recent map. And you can see with the wind barbs and the height contours how that flow is basically parallel to the height contours with lower pressure to the left. And this is basically showing that we have all three of those accelerations more or less in balance. And that's a very typical situation for upper air flow patterns, especially in the mid-latitudes. And so that's what we call the gradient wind, where the wind is basically responding to the pressure gradient. And even with the turning of those height contours, the flow will turn in response. So the gradient wind, all three of these forces or accelerations are important and need to be kept track of and non-zero. And so we get back to the situation where we first started, where we might have some sort of turning, in this case cyclonic, counterclockwise with a positive radius, and a balance between a pressure gradient force, Coriolis, and centrifugal acceleration that would satisfy this force balance. So in order to figure these out, we need to look at the equation. And the equation of motion here, you can see, is if we want to solve for this v, we want to solve for the wind speed, we basically are trying to solve a quadratic equation. So we got minus v squared over r minus fv minus d phi dn equals 0. And that's very much a quadratic. It's like ax squared plus bx plus c equals 0. So the quadratic formula to solve for x hopefully is familiar. Minus b plus or minus the square root of b squared minus 4ac. I forgot to put the square root in there. Over 2a. So in our case, the variable we're interested in solving is v. And then the a term is minus 1 over r. The b term is minus f. And the c term is minus d phi dn. So we can plug those in and solve for the gradient wind. So v is equal to minus fr over 2. Okay, so you can see that's they've basically combined minus b and divide by 2a. And then plus or minus the square root of f squared r squared over 4 minus r times d phi dn. So notice here that this first term that's inside the square root, f squared r squared over 4, is the outer term, fr over 2 squared. Okay, so you can see that we might be adding and subtracting very similar terms. But that's always going to be modified by minus r d phi dn. Now, as you might expect, this expression has a number of mathematically feasible solutions, but not all of them are physically realistic. The main constraint that we have is that the velocity has to be a positive number. Well, either 0 or a positive real number. So we can't be dealing with the square root of a negative number. We can't have imaginary numbers. And the overall result has to end up being greater than 0. But you can imagine, at least if we're just going to focus on the northern hemisphere, where f is positive, we can have a variety of combinations of r and d phi dn, and then these plus or minus roots to give us several possible solutions. So the d phi dn can be positive or negative. The radius can be positive or negative. And then we have this plus or minus root in the solution. And so you multiply those out. We have 8 possible combinations of solutions that we need to consider. So we'll sort of break this down. We'll look at the different combinations where d phi dn is greater than 0, and then we'll look at the ones where d phi dn is less than 0, and kind of plow through this. So let's first consider d phi dn as a positive value. We're just going to focus on the northern hemisphere, so let's assume that f is always positive. And let's look at the r, positive r, the cyclonic curvature first. Okay. So I'm going to kind of work from the inside square root out with this analysis. And so since both r and d phi dn are positive, then this term r times d phi dn is positive. And notice that we are subtracting that from another positive value, f squared r squared over 4. And so since we're subtracting a positive from this value, and this, if we take the square root of this, is the absolute value of fr over 2, then the net result of subtracting this and taking the square root is that this term is going to be less than fr over 2. Okay, and since we're doing that, the square root is less than the absolute value of fr over 2. And so we're adding and subtracting a number that's less than fr over 2 to minus fr over 2. And we're going to end up with a negative v in both cases. Okay, so f's positive, r is positive. That means minus fr over 2 is negative. And we are adding and subtracting to that a value that's lower than fr over 2. And so we're going to end up with a negative number in both cases. And since both of these solutions are unphysical, we really can't have this situation. We can't have this positive r and positive d phi dn. And so those we won't consider because they're unphysical. So sticking with this positive d phi dn, let's look at a negative r. Okay, and again, f is positive. So r d phi dn in this case is negative because r is negative, d phi dn is positive. However, fr over 2 with the minus sign ends up being positive. Okay, so minus fr, f's positive, r is negative. The minus sign makes the whole thing positive. So if we look at the square root term, this r d phi dn is actually negative, and we're subtracting a negative. So we're actually making this overall term, after we take the square root, a larger value than FR over 2. Okay, so we're taking F squared R squared over 4 and basically adding a number to it, adding a positive or subtracting a negative. So after taking the square root, we got a bigger value than the absolute value of FR over 2. We are adding and subtracting that from this positive number, FR over 2 with the minus sign. So as a result, we're going to end up with one of those. We're basically taking a positive and adding a positive. We're getting a positive V. That's a physical result, and that's good. So we can analyze that one. The negative root, though, we're taking a positive and subtracting a value that's actually larger. That ends up with a negative V. That's unphysical, and we don't need to consider it. So let's look at the force balance diagram in this case, where we end up with a physical solution where dphi dn is positive, but R is negative. And we call this an anomalous low, and it's the positive root of that situation. Okay, so with a negative radius of curvature, that's a clockwise turning, that's an anticyclonic turning of the flow. And in that case, we look at the top of that circulation, the wind's going to go from left to right. That's the orientation I've been using mostly. So the n hat direction is off to the left. And dphi dn greater than 0 means that higher pressure needs to be in that direction and lower pressure in the minus n direction. So the pressure gradient force here is going to act to the right. The Coriolis force also acts to the right, since we're in the northern hemisphere. And that means the centrifugal acceleration has to act to the left and counterbalance pressure gradient and Coriolis. So our force balance diagram ends up looking like this. So what we see here is anticyclonic flow around a low pressure center. And this is rarely observed. We typically don't see this, this clockwise circulation around a low, but it's at least physically possible. And similar to the cyclostrophic example, where we could see that anticyclonic rotation around a low center. So negative R in this example. That's also physically possible and is observed on occasion, but it's rare. So now let's consider the negative dphi dn and those combinations. And we'll start with a positive R. Okay, so this is the cyclonic turning. This is the counterclockwise rotation. And so if R is positive and dphi dn is negative, then R times dphi dn is negative. And we subtract that negative in the square root. And so that's going to make this term larger than the absolute value of FR over 2. But this first term is negative because R is positive. So we have two positives multiplied by a minus sign. So this term out front is negative, and we're going to add and subtract a term that's larger. So we're going to have one physical solution with positive root, and then one unphysical, ends up with negative V, the negative root. So let's consider the force balance for that positive root. And this is what we would call a regular low, where we have the cyclonic counterclockwise turning around a low pressure center. Okay, so R is positive. We get that counterclockwise turning. Let's look at the bottom part of that where the wind's going from left to right. Centrifugal acceleration is outward. The Coriolis is to the right as well, both those in the minus n direction. And that needs to be balanced by the pressure gradient force acting to the left, and that's the case where you have d phi dn negative. That means that the pressure is decreasing in the n direction. And so this is the typical situation where you have this cyclonic turning. You should have lower pressure to the left of the flow. Now let's consider d phi dn also negative, but r is negative. So this is the anticyclonic or clockwise turning situation. So r d phi dn, multiplying these two negatives gives us a positive. So we need to look at this term inside the square root, and we're subtracting a positive from f squared r squared over 4. And we could have a situation where this this r d phi dn ends up being larger than f squared r squared over 4, and that would make this term inside the square root negative, which would give us an imaginary number, and that's not a physical situation. So in this case, we have to consider a constraint where this term f squared r squared over 4 is greater than r d phi dn. If that's the case, then the term inside the square root will end up being smaller than the absolute value of fr over 2. And with the negative r, I forgot to mention, then minus fr over 2 is positive. So we're going to be adding and subtracting to that a value that's smaller than this first term. And so we should get a physical situation in both cases. So minus fr over 2 is positive. We're adding a smaller positive number to it. That ends up with a positive. And the negative root also works. Minus fr over 2 is positive. We subtract a smaller value than that. We still end up with a positive v. So we need to consider force balance for both situations. And so let's take a look at that. So with the positive root, the actual larger velocity, again, d phi dn is negative and r is negative. So that's a clockwise turning, that's anticyclonic turning. If we look at the top of that circulation, the wind's going from left to right. d phi dn is negative, so lower pressure should be in the plus n direction, and higher pressure in the minus n direction. So it's the flow around a high pressure center. And we should see the force balance like this. The Coriolis acting to the right, pressure gradient force pointing from high to low, and centrifugal pointing outward from this turning. Now that positive root, we end up with a value of v that's greater than minus fr over 2. Okay, so going back and look at the solutions, remember minus fr over 2 is positive, and we're adding some positive number to it. So that ends up being greater than minus fr over 2. And the reason why this is an anomalous high is that this larger value gives us a relatively large centrifugal acceleration. And we can go through and analyze these terms to prove that that's the case. Okay, and so if v is greater than minus fr over 2, we can multiply and divide by well, you can multiply both sides by minus 1 over r, since r is negative. You see minus v squared over r is greater than fv over 2. And since these are counterbalancing accelerations, the centrifugal, if we consider the absolute values of those, this is saying that the centrifugal acceleration has got to be larger than the Coriolis acceleration divided by 2. Okay, so that's the outcome of this positive root, is that we have a relatively large centrifugal acceleration. Now the force balance says that the Coriolis has to be balanced by the pressure gradient force plus the centrifugal acceleration. And I'm using the absolute values of these just to simplify the situation. Okay, but Coriolis is pointing to the right, pressure gradient and centrifugal are pointing to the left. Now what we just analyzed, if we multiply both sides by 2, is that 2 times the centrifugal acceleration has to be greater than the Coriolis, greater than or equal. So that means that the centrifugal plus the centrifugal is greater than the Coriolis. We can plug this back in, substitute that in for the right-hand side. So 2 times the centrifugal is greater than the sum of the pressure gradient and the centrifugal. Canceling out one of these centrifugal, we see that the centrifugal has to be greater than or equal to the pressure gradient force. And so that's saying that we have a relatively high wind speed and relatively low radius. And so the centrifugal acceleration on this left-hand side has to dominate. And that's unusual. That's not what we typically see. So that positive root is actually not the usual solution. The regular solution is the negative root, the smaller value of v. So we still have Coriolis acting to the right, pressure gradient, and centrifugal acting to the left, and those are in balance. So basically the same situation, at least the same direction for these accelerations. But in this case, the centrifugal is less than the pressure gradient force. So you can see the pressure gradient force is larger than the centrifugal. And this is the typical situation where we see this clockwise turning, this anticyclonic turning of the flow around a high pressure center. So if you're going to look at actual maps and try to estimate the values of the gradient wind, you should use the regular high, regular low formulas, where the negative root for the regular high and the positive root for the regular low, to get those values that we typically see. And going back to making sure that the term in the square root is not negative, this actually puts a limitation on the pressure gradient force for high pressure systems. Okay, so again, we're looking at negative d phi dn, negative r, and northern hemisphere situation. So r times d phi dn ends up being positive. And since we're subtracting that, that has to end up being smaller than f squared r squared over 4. Okay, so we have to have this situation in order to get a physical solution. And so we can rearrange, take the absolute values, divide by r. Since r is actually negative, let's consider absolute value of both d phi dn and r, and just look at the magnitudes of those. And this is the resulting constraint, that the height, the geopotential height gradient, has to be lower If it's equal, then that term in the square root ends up being 0, but it has to be less than the absolute value of r times f squared over 4. So you can hopefully see the constraint here is that the smaller the radius gets, the smaller the pressure gradient has to be. So as we approach the center of curvature and we get to smaller and smaller radii, this d phi dn has to get very, very small. And that means that we should see a weak pressure gradient force and therefore weak wind speeds near the center of high pressure systems. And in fact, we do observe that. And notice there's no such limitation for low pressure systems. We didn't have to worry about this negative square root when we're considering a low pressure system. And so d phi dn can be whatever it wants to be, whatever it needs to be to get the wind speed near the center of curvature. So I just pulled the sea level pressure map just to show an example. We've got a pretty strong low pressure system in the Gulf of Alaska. And you can see that the pressure gradient in the vicinity of the center of that low is relatively large. But then we also have a large high pressure system over the northern plains. And notice there's hardly any pressure gradient at all near the center of that high pressure system. So this is the reason. So that's the end of the lecture. You should look for the next homework assignment, and we'll continue this when I get back on Thursday.